Okay.
Okay. Hello, everyone. Thank you for joining GeoScience and GeoEnergy webinar of today, 28th of May, 2020. These webinars are hosted by Sebastian Geiger at Heriot-Watt University and myself from TU Delft, Netherlands. We are especially grateful to our keynote speakers who have supported this initiative for good cause, and to you all to join us and combat the work from home isolation. We are all proud members of the global geoscience community. Please subscribe to our YouTube channel and help us spread the words. All previous lectures are available on our YouTube channel. Now to the lecture. It's our pleasure and honor to announce our keynote speaker of this week is Professor Ruben Juanes from MIT. Ruben is a professor at the Departments of Civil and Environmental Engineering and also Earth, Atmospheric, and Planetary Sciences. Ruben obtained his undergraduate degree diploma in civil engineering from the University of Coruña in Spain, his first home country, then moved to the USA, California, and obtained his master's and PhD degrees, both in civil and environmental engineering from the University of California at Berkeley. Immediately after his PhD, he became assistant professor of energy resources engineering at Stanford University, but then left Stanford after about 2 years to become assistant professor at the University of Texas at Austin. He did not settle himself for longer than even a year in Austin when he decides to join MIT, first as assistant, then associate, and finally professor of civil and environmental engineering. His remarkable career is full of awards, just to name a few: Department of Energy Early Career Award, Department of Energy Award for Outstanding Contributions in Geoscience, ARCO Professorship in Energy Studies from MIT, Gilbert Winslow Career Development Professorship from MIT, and Astor Visiting Lecturer at Oxford University can be just mentioned here. He was chair of the Gordon Research Conference on Flow and Transport in Permeable Media in 2018. He has given a number of keynote lectures in several prestigious scientific events. Ruben is a world-leading geoscientist with a strong interest in the physics of multiphase flow in porous media. His innovative research focuses on advancing our fundamental understanding and predictive capabilities of the simultaneous flow of two or more fluids through rocks, soils, and other porous materials. Research in his group combines theory, simulation, and experiments that elucidate fundamental aspects of multiphase flow, which are then applied to predict large-scale Earth science problems in the areas of energy and the environment, including geological carbon capture sequestration, methane hydrates, and ecological of arid environments. It's our pleasure and honor to host Ruben as our keynote speaker. Please note his lecture will last for about 30 minutes, followed by questions and discussions like before. Please type in your questions in the chat room, and Sebastian will go through them after the talk. Ruben, thanks again for your kind accepting of our invitation. The stage is yours.
Thank you, Hadi. I mean, it really is a pleasure. Thank you so much for the kindest introduction. I'm delighted to be here, be part of this webinar series. It's great that you're doing this for the porous media community. And as I said, really excited to be part of it. I mean, after your introduction, I'm not sure that there is anything else that is left for me to say, but I'll try for the next half hour or so. What I will be discussing today is some recent work on the topic of wettability, and in particular, how wettability affects the interplay between multiphase flow and granular mechanics. This is especially towards the end of the presentation, the work of two of my current PhD students, Olivia Amon and Barjan Prinkulov. But the presentation will be peppered by slightly earlier results, contributed mostly by former students of mine who have gone to greener pastures and done great things. Amir Palavan, who is now a postdoc at Princeton, Ruben Juanes, who is an assistant professor at McMaster, and Chris McMinn, who is a professor at Oxford. So usually I start my presentations, many of my presentations, with this slide, and this is really just to illustrate the very profound impact that capillarity has on porous media flows. So what you see, and I don't know if you can see me moving the mouse through the slide. Sebastian or Hadi, could you let me know? Can you see it?
Yes, we can see it.
Okay, good. So now I know that I can point to things on the slide. So what you see here on the top frame is a porous medium, just a pack of glass beads with two different fluids, water and glycerol. Water is dyed blue for visual contrast, and these two fluids are miscible. They mix in all proportions, and water is lighter than glycerol is. So as you can imagine, if we let the system go, well, the water will tend to run up and the glycerol will tend to slump down. But this process takes place in the form of a smooth, we could call it interface. There's no real interface, but a diffuse interface between the two fluids. So if we replace the fluids by two fluids that are not miscible, they are immiscible, say air and water, of course, what we expect is that the air will also tend to run up and the water will tend to slump down. But the way in which this happens is very different. Right? What you see is that initial vertical interface, there's a portion of it that remains static and does not move, and does not ever move. It is not a question of time scale. So clearly capillarity is playing an important role. And this doesn't need to invoke or involve complex effects like contact angle hysteresis or anything like that. So in this system, we have one fluid that is strictly wetting, is completely wetting, and the other one that is completely non-wetting. And there's no contact angle hysteresis. Yet we see this spinning effect. And if we zoom in, and here we use sort of an analog system, this is a microfluidic chip in which we can image the individual interfaces. Just from the physics of fluid-fluid displacement, for the non-wetting phase to displace the wetting phase, it has to squeeze through the pores, and that requires a certain curvature. So you have that interface has to squeeze through that opening. Whereas for the wetting fluid to advance, something very different needs to happen. It doesn't need to squeeze through anything, it needs to hug the posts, and that occurs at a very different curvature. So curvatures, of course, translate by the Laplace equation into pressure differences across the interface. And what we conclude from this is that the pressure difference for drainage, that is for the non-wetting phase to invade, and for imbibition, that is for the wetting phase to invade, those two pressures are very different. And the difference between them is taken up by a gravitational potential, and that is why we see a static interface in which neither drainage nor imbibition occurs. So what this presentation is going to be about is the impact of wettability on this type of processes. So wettability is a notion that is familiar to everyone. So we see there on the left figure a situation in which the water spreads on a surface, and we say that the surface is wetting to water. On the right frame, we see a situation in which the water is the non-wetting phase, and it beads up on the surface of this lotus leaf. So the outline of the talk, and hopefully I will get to everything that I want to cover in the time that I have, is we will see some examples of how wettability plays a role in first smooth systems, so systems where everything can be visualized nicely and the physics are rather constrained, but nevertheless very interesting. Then we will introduce some complexity by adding disorder to the system, and then finally we will see how these multiphase flow effects play a role in the mechanics of granular packs. So this is the first example that I would like to introduce, and that is, I mean, it doesn't really get any simpler than this, I would say. So I have one fluid displacing another in a smooth, round, cylindrical capillary tube. And we know that if we inject, in this case, it's air displacing viscous fluid. If we inject air at a low rate, then all of the viscous fluid is displaced and the interface advances and displaces the viscous fluid completely. If we inject at a higher rate instead, and this is of course very well known, we leave a film of the viscous fluid adhered to the walls of the tube. And you can see there that some subsequent effects happen as a result of the leaving that film of viscous fluid behind. So one of the questions that is important to address is how does the wettability of the capillary tube affect this process, in particular the transition from leaving no film to leaving film behind the meniscus. And what we see is that for a hydrophilic tube, that transition, not surprisingly, occurs earlier meaning at a lower capillary number, at a lower injection rate than when we have a hydrophobic tube. So one of the important observations is this dichotomy between the interface or the meniscus advancing and the contact line advancing. So what I'm going to show is 3 simultaneous videos. They correspond to experiments at different injection rates. And what you see is that because of the injection rate is different, well, the progression of the meniscus, of the lead meniscus, occurs at a different speed. But I will play this again. Even though the injection rates are very different, the contact line advances at the same speed. So we conclude from this that there is a decoupling between what happens at the contact line and what happens at the leading meniscus. And that is an interesting observation because it allows us to model what happens near the contact line, irrespective of, independently of what happens at the leading meniscus. So one can develop a theory for how that thin film essentially de-wets, and this accounts for the mobility of the two fluids, the partial wetting effects, and the fact that this is a round geometry. So I'm not going to get into the details of how this equation is derived, but it allows us to make predictions of the thickness of this thin film, of this rim, as a function of space and time. And we can compare those predictions with experiments and conclude that the theory agrees well with the experiments and allows us to determine the time at which that rim is going to snap. So this lends itself, this is, I would say, almost like a side note, but an interesting one, at least to people like me. And that is this topic of how does the pinch-off actually take place. This is I mean, of course, a classic topic in fluid mechanics with very deep and interesting results. So for instance, it has been determined, it's now known, that the process of a droplet falling of a faucet is a universal process. You can repeat the experiment with a fluid with a different surface tension, with different density, with different viscosity, and you can collapse all of that behavior of how the neck of that droplet snaps into a single universal behavior. So this is very well known by now. It came as a surprise that if you reverse the experiment, that is, if you release a bubble in a bath of a viscous fluid, that process is not universal, meaning that the timing of the pinch off and the details of how that pinch off takes place actually depends very strongly on the initial and boundary conditions. So any non-uniformities or any perturbations in the system are going to affect deeply how that pinch off takes place. And that came as a surprise, but it's now known that this is known to occur, that this process of bubble pinch off is non-universal. So what was surprising here is that by adding confinement to that system of bubble pinch off, we restore universality to the pinch off process. And the details of why this happens is in itself an interesting story. I would summarize it in the following way. The pinch off process consists of two regimes, one leading to the rim growing and the neck thinning, and then the actual process of the pinch off. So the immediately before pinch off, that process is described by self-similarity of the second kind. Maybe this will mean something to some of you. This is a process in which the system remembers the history, remembers the initial conditions. So this is entirely consistent with this idea that the process of bubble pinch off is not universal. However, this process is preceded by this neck extension and rim growth, and that happens to be described by a self-similarity of the first kind. So the way, in a loosely speaking, the pinch off process first goes through a regime that forgets all the memory and then enters a regime that would remember the memory, but by then there's nothing to remember. And this is how confinement leads to a universal pinch off process. That is how a bubble pinches off in a universal fashion inside a capillary tube. So this is work by Amir Palavan that was published a little while ago. So far I've talked about perhaps the simplest configuration, which is a capillary tube. The next simplest would be to allow for one of the spatial dimensions to be larger. So if we have a microchannel, for instance, we can try to unravel some of the effects of wettability on fluid displacement in that geometry. And of course, we would not be the first ones to look at this. I am highlighting here a study that was very influential for us. This was published a few years ago now. This is work by Denis Barthelot and his group. And what they did was to revisit the Safman-Taylor problem. That is, they injecting a low viscosity fluid in a microchannel to displace a high viscosity fluid that is known as leads to the Safman-Taylor finger. When it leads to the Safman-Taylor finger, when the fluid that you inject is less wetting, actually when it leaves a film of the viscous fluid coating the surfaces of the channel everywhere. So what they decided to do was to repeat this experiment, to revisit it, but now making the low viscosity fluid that is being injected the more wetting fluid. And what you can see now very clearly from from this figure is that something very different happens. So the morphology of the instability is very different. And if you inject at a sufficiently high rate, the formation of the main finger is actually preceded by the formation of a thin, we could call it a pre-wetting film that runs ahead of the finger. So what we decided to do was to essentially take this system and add some disorder to it. So this could be easily achieved with soft lithography techniques. So we have a microchip that is patterned. It is like a helical cell, but with posts in it that can be fabricated very precisely, again, using soft lithography. And what is special about this system that we borrowed from Bartolo's group is the use of a polymer to construct the chip that is that responds to UV radiation. So the surface energy of this material will change with exposure to short wavelength UV. And the result of that is that the wettability can be precisely tuned with UV exposure. And this gives us the ability to go from a system in which water is strongly non-wetting to a system in which water is very strongly wetting. So the result of that study can be summarized in this visual phase diagram, in which we have two axes. So on the x-axis we have different wetting conditions, and then on the y-axis we have different injection rates, from low injection rate at the bottom to high injection rate at the top. So we could spend some time kind of dissecting what is going on in this diagram, but in the interest of time, we will not do that. I will just highlight one particular observation, and that is that if we fix the injection rate, as we have systems with different wettability, there is a point at which transition occurs from a morphology that is dominated by pore invasion. The fluid that is being injected invades the porous medium, the helical cell, in a pore by pore fashion. So the invasion of one pore leads to the invasion of some neighboring pore. So there's a transition from that type of pore invasion morphology to one that is very different, and I will illustrate it with a couple of videos here at a relatively high capillary number or injection rate. This is the way in which the displacement takes place, not by invading pores, but by coating posts. And the coating of one post will lead to the coating of a neighboring post. And if we, now in an accelerated, sped up movie, if we represent what is happening at low injection rates, we see the same type of process, but now leading to avalanches. So the fluid that is invading first coats the posts. Those films will swell, and at some point they will swell sufficiently to give rise to an avalanche of these post-coating invasion events. So from statistical physics point of view, you could think of this as an invasion percolation process, but in imbibition instead of drainage. Okay, so this sets the stage for, I think now, talking about the last aspect that I wanted to touch upon today, and that is how these capillary interactions and wettability effects play a role in the displacement of one fluid by another when the porous medium itself can deform. And there are there's one basic idea, and that is that the displacement can take place either by, say, squeezing through that rigid pore geometry that we have initially, or by modifying that geometry and opening conduits that will lead to the displacement of the fluid that is being injected. There's been really an amazing body of work that has been done over the years in this context. I'm just highlighting here, not really only just a couple of examples, work by the Oslo group, and then Bjørnar Sandnes, having moved to the UK, work by Chris McMean, work by Varas, but these are, again, just illustrative examples. We study this type of systems of granular packs that can move, again, in a simple tabletop configuration. So we have a helical cell that we pack with, in this case, with glass beads. And now there's one aspect that allows us to control an important determinant in the system, and that is the confining stress. So by having a lid on top of the granular pack and putting more or less weight on that lid, we can control that confining stress. So we did some early work in this type of systems, and that was, again, we learned a lot from it back at that time, because we realized that we could see the different patterns that could emerge as a result of the balance of forces at the pore-scale. So there are some forces that act in the direction of opening conduits, and forces that act in the direction of preventing those openings from occurring. In our systems, we didn't have cementation between the grains, so the only forces that were resisting granular motion was just simply friction. But frictional forces, of course, depend on the level of confining stress. So we arrived at two dimensionless numbers, some modified capillary number that essentially depends on how fast one is injecting, and then this balance between forces promoting fracturing, promoting grain dislodging, and forces preventing it. So we call this the fracturing number. And what we realized was that these two dimensionless groups, or dimensionless numbers, were sufficiently to, at least at first order, determine what type of invasion morphology one would arrive at. In particular, it was interesting to us that the transition to the fracturing regime could occur at very small, even vanishingly small injection rates, as long as the fracturing number was high enough. And this is something that, at the time we termed capillary fracturing, because it's different from the viscous dominated fracturing that you can associate with, say, processes like hydraulic fracturing. So the question then becomes, well, how does wettability play a role, if at all, in this process? And the short answer is that it does play a role, and it seems to play an important role, at least in some regions of the parameter space. So what I'm going to show here is 3 videos. On the left, we're injecting a low viscosity fluid into these granular packs, and that fluid is less wetting than the defending fluid. So this is a drainage invasion. And what we see is this viscous fingering-like invasion pattern that leads to eventually fracturing as the pressure builds up, to fracturing of the granular pack. If we maintain the conditions the same, but all we do is change the fluid pair so that the fluid that is being injected is more wetting, so we're in a weak imbibition injection, this is what we observe. So as you can see, the invasion morphology is very different. It is dominated by this very robust and hierarchical fracturing process. And you could think, well, this is only going to get stronger if we have strong imbibition. But in strong imbibition, when the fluid that has been injected is super wet into the substrate, to the porous medium, then no fracturing at all occurs. And we now have a better understanding of why this is. The fluid is so wetting that it will just immediately coat the grains of the granular pack and will not provide any of the black and pressure support that is needed for fracturing. Okay? So this is sort of a comparison of the three regimes as a function of wettability. And what we've done recently, and I will try to be brief over the next few slides, is what I will try to describe quickly is our recent efforts in trying to better understand why this happens and better model it. So there are two ingredients to this. One is a model for the fluid-fluid displacement. So we built on the work, classic work by Chiplak and Robbins, which for a quasi-static fluid-fluid displacement, they described how the advancement of the injected fluid could occur by different type of pore fluid or pore level instability events, burst, touch, and overlap, to account for the entire range or the full range of wetting conditions. There's another type of pore level event that can play a role. We call that corner flow. And here what I'm illustrating is the effect that wettability then has on this very slow quasi-static displacement, going from strong drainage, where you have essentially something akin to invasion percolation, to weak imbibition that gives rise to a very compact morphology. And then in stronger imbibition, then corner flow starts to take over. And for very strong imbibition, that is the favored mechanism by which the fluid entrains in the porous medium. So we have now an understanding of, or a way to model a quasi-static fluid-fluid displacement, but we know that that is not enough. We need to be able to model that pressure transient, and this was done by extending the analogy from single phase flow in a porous medium to an electric circuit, extending single phase flow analogy to the two-phase setting, in which the presence of interfaces really act as capacitors. This is, in my mind, a brilliant idea by Barjan Primkulov. So we now have electric circuit with resistors, capacitors, and batteries that allow to account for the motion of interfaces through the pore space. This has recently been published and allows us to now not only reproduce the whole range of morphologies that take place as a function of capillary number and wettability, but also something that remains to be explored experimentally, really, and that is the pressure fluctuations that can occur in different wetting conditions. So that provides one of the two ingredients. The other ingredient is the grain-to-grain interactions. So this we deal with using a discrete element modeling approach, where the grains interact following Newton's law of motion for linear and angular momentum. And this evolution of forces between grains is, of course, coupled in a two-way fashion. It's two-way coupled to the pore fluid. And it is two-way coupled because if we increase the pore fluid pressure, that is going to change the forces that act on the grains. And if we change the morphology or the geometry of the pack, that is going to lead to pressurization or changes in the pressure in different pores. So having that model allows us now to look at the injection of one fluid to displace another in a granular pack that can move. So we will now have different initial conditions controlled by the packing density, going from a rather loose pack to a rather dense pack. And we're going to investigate here injection rates that are very low, so that viscous effects are really negligible compared to capillary effects. And this gives rise to, I mean, again, a rather rich set of fluid solid displacement morphologies. So as a function of the initial packing fraction from loose to dense pack, and as a function of wettability from a drainage displacement to an invasion displacement, we see a whole range of different invasion regimes. So what I will do is I will concentrate on one of them, this one occurring here at sort of at some intermediate conditions, that is dominated by first the expansion of a cavity, followed by the emergence of fractures from that cavity. So this is something that now you see illustrated here in these time-lapse videos of the simulations. And what we want to better understand is this observation of having different times at which the fractures emerge as a result of different wettability conditions. So what we see is that fractures emerge earlier, the onset of fracture occurs earlier in imbibition than it does in drainage. And this is not something that can be immediately attributed to the evolution of the injection pressure or to the evolution of the packing fraction, because those transitions occur at different, not only different times, but also different values of injection pressure and packing fraction. But what we do see is that we have a transition from a system that behaves almost like a fluid, let's say a granular fluid, to a solid, so that is a transition that is akin to jamming in soft matter physics. So there's been a lot of work that has been done on this jamming transition, and we can borrow some of the techniques that have been developed to characterize it. So for instance, the mean contact number or the mean particle stress throughout that transition. And indeed, what we see is that if we plot the mean particle stress, for instance, as a function of packing density, what we observe is that so these curves for different conditions, for different contact angles, will be on top of each other, but the transition from one regime to the other will occur at different points, one that we can characterize. And this is, now we can think of our system in terms of the classic jamming phase diagram, where we have the packing fraction as one of the axes, the injection pressure as another, and one that we really have not investigated, which would be pressure fluctuations, which in the jamming literature is denoted by temperature. So we can now test whether this idea holds in our system. So we can plot for different initial packing fractions, the evolution of the packing fraction, and the evolution of injection pressure, and mark the point at which the jamming transition occurs. And we can do that for different initial packing fractions. And what we observe is that all of those transitions occur on a single curve. So we can now sort of universally separate our parameter space into a jammed region that will be controlled by fracturing, and an unjammed region where the fluid invasion will be controlled by cavity expansion. And with this, I will finish. I will just illustrate some time-lapse videos of the simulations for the various regimes. So we see here this cavity to fracturing transition regime at smaller contact angles and at relatively low packing fractions. We observe a different regime altogether. So this is illustrated here. We don't see the initial cavity expansion when the system immediately turns into the formation of conduits that I wouldn't qualify as fractures, but rather as fingers. And this is very similar to a behavior that has been reported before and has been termed frictional fingers. What happens when we have strong imbibition? Well, if we have high initial packing fraction, then that granular pack is essentially not going to move. So we revert back to this condition that is controlled by a rather sort of a stable or compact fluid invasion of the injected fluid. That is something we term capillary invasion. And something interesting happens under these conditions, but lower initial packing densities. So this is illustrated here. So it looks similar, but because the initial packing density is lower, some of the grains near the interface are going to be sucked into the invading fluid in morphology that we term capillary compaction. Okay, so in conclusion, and I think I've gone a little bit over my time, I would just simply say that wettability plays a fundamental role in fluid displacement in porous media. That is such a vanilla statement that I hope everyone will agree. Some of which, so despite the fact that this is a rather obvious statement, many of the implications are still, or many of the physics underlying those effects are still poorly understood. And then more specifically, what we've seen is that the emergence of fracturing and other hydromechanical patterns like frictional fingers and capillary compaction can be explained as a jamming transition, which again I think is an interesting way to borrow a lot of the work that has been done in soft matter physics into our world of fluid displacement in a porous medium. So with that, I will stop. I'll be happy to take any questions if there are any. Thank you.
Thank you very, very much, Ruben, for an excellent talk. So we do have plenty of questions that are coming in online, so I'm just trying to go somewhat chronologically and topically through them. So going back to one of your introductory slides, Maximask isn't pinning one of the reasons for contact angle hysteresis. You made a comment, these interfaces are quite stable and it's not hysteresis, but pinning.
Yes, I mean, I think the answer to that question is yes, the fact that you have the fact that you have pinning, that you have an advancing and a receding contact angle that are different, and you can have stable state in between. That is a source of contact angle hysteresis, yes.
And then, Soren Pop asks, also going back to probably the same slide 2, is gravity playing a role in the experiments you showed right at the beginning?
Yes, indeed. So gravity is playing a role, because otherwise the light fluid would not go up and the heavy fluid would not go down, right? So if we were in a microgravity environment, none of this would happen.
And it just follows up on slide 5. H has a non-monotonic profile. Is this non-monotonicity induced by the initial conditions, or are there higher order derivatives involved?
Yes, sorry. Yes, there are higher order derivatives involved. Yeah, fourth order.
Thank you. So, staying on the topic of boundary conditions, and so a bit about the really nice experiments you've run, King Yuan asks, what are the boundary conditions in these radial geometries that you showed in your experiments?
Yeah, so I will preface my answer by a cheeky comment. You can see that all of our experiments are radial, right? So the reason why they're radial is because we don't know how to do linear displacement experiments. I mean, that is true. It is harder, we find, to have reproducible experiments when we have linear displacements. This is something that we can revisit. So radial displacements allow you to not have to worry about uniformity of the initial front as you deliver the fluid, because it's injected at a point. So you still have to do this carefully and design the injection port carefully, but it brings in fewer issues in our mind. And then at the perimeter, what we have is, in order to avoid end effects, is we submerge slightly the cell into the defending fluid, into a bath of the defending fluid. And that will guarantee that there will be no interfaces there, and so no capillary end effects, and that the pressure will be perfectly constant.
And another question about your experiments. In slide number 19, are the viscosity ratios the same for all fluid pairs?
So I don't know what was on slide 19, but I can almost guarantee you that they were not, because I think all of the experiments that I showed, all of them, are for unfavorable viscosity contrast. So when the fluid that is being injected is much less viscous than the defending fluid. Typically, we use viscosity contrast in the order of 100 to 1,000.
To sort of some of the results now, there's a question from Shahriar Al-Khazali. Thank you for the talk, Ruben. Experiments in Berea and torpedo sandstone suggest that the lowest residual oil is achievable at slightly water-wetting systems. Do you observe the same tendency in your experiments? Yes, we observe exactly that. And the underlying mechanism is this cooperative pore body filling. I think that was, clear both from the pore network simulations as well as from these microfluidic experiments. So you go from a invasion percolation type displacement, in which the front is rugged and you can leave actually a lot of fluid behind, to morphology that is where the front is much more compact and essentially leaves in the system, in the simple quasi-2D systems, leaves no fluid behind. So yes, indeed, we observe the same thing. Okay, thank you. There's one further question around your experimental work. It's somewhat related to this. So, Jan asks, it's very interesting, modified micromodel and beautiful images. She she or he clarified later on, said, I wonder how long the wettability of the polymer coating lasts, and does it have any reactions with organic fluids, the silicon oil, the decane?
Yes. So it's not a polymer coating, it's UV radiation, but it has a lifetime, just exactly as you suspected. It doesn't last forever. So there's a wettability alteration. One of the things that we're very careful about is in order for it to be precise. So we conduct the experiment set time after we expose the polymer to UV radiation. I can't remember now, but it's something like 4 or 6 hours. That's when we conduct the experiment too, because the wettability alteration, as I said, is not permanent. So if we wait 2 days, then the contact angle would not be the same. Now, you also mentioned, well, what fluids can you use? Can you use just any fluid? And the answer is no. This No81 polymer has also certain compatibility with fluids and incompatibility with others. So we would have to see exactly what fluids you're interested in, and we could tell you a little bit more. One thing that we did find, and we found out the hard way, is that as the surface is exposed to UV light, well, it changes the surface energy, and the surface, it then is prone to some surface chemistry as a result of it. So we found the hard way that there would be some radicals on the surface that would react with fluorescein. So our first batch of experiments were done with fluorescein in the injected fluid, water, and we found that fluorescein was reacting with the surface. So we were, from a visualization standpoint, we were losing mass. We were losing water just as a result of the fluorescein reacting. Yeah, that was a tough day for my then student, Robin, who realized that he had to repeat all the experiments. Yeah.
A question from Serena Dairy. Is the recess in porous media flow can be significant? In your flow study in the formable porous media, I was wondering, one, what would happen if you would inject and produce fluid cyclically? And two, would the number of phases play an additional role?
Yeah, so those are great questions to which I don't have an answer other than to say that it is indeed very interesting. At all levels, from even for a rigid pack, having these injection extraction cycles. Of course, there's been some work done, but really a lot would remain to be observed and characterized. And if you have deformation of the medium, again, that adds a layer of complexity or richness in the physics that we haven't touched. It would be very interesting to do so. That's really all I can say. That it would be great to look at that. Yeah.
So related to this is the question from Abai. Thank you for the inspiring talk. Is there any ongoing plan to examine the wettability effect in your group?
At the microscale, it really depends on what you mean by microscale. So some of the metrics that we arrive at, we call them microscale metrics because they really are not pore level, right? So they reflect how the system is behaving overall. So for instance, the amount of trapping or the front roughness, the efficiency of the sweep, things of that nature. If by microscopic you mean using, for instance, a rock core, then the answer is probably not. That's not what. There are other people who do that a lot better than we do.
Around the fracturing, we have a question from Hossein Nassab. Thanks a lot for the talk. In slide 17, you show that the fracture number can help you to investigate the impact of wettability during imbibition. Is that right?
Yeah, okay, so that's a very good question. The fracturing number that we defined was defined for purely a drainage system, a drainage injection. So to be perfectly honest, we haven't been able to extend the fracturing number to systems that cut across different wetting conditions. So we're thinking about it. I mean, we keep thinking about it, but we haven't been able to arrive at a natural extension of the fracturing number for different wetting conditions. So, very good question.
And staying on the topic of fracturing, Mahani asks, and thank you for the talk, Ruben. Your findings are valuable towards better understanding of fracturing in soft rocks. Just for my understanding, what's the orientation of the minimum stress in your experiments?
Yeah, so what you see is, that's a very good question. What you see is that and we try that there's no preferential anisotropic stress on the plane, right? So we try, and I think we do succeed in having a rather isotropic stress state on the plane. And then we are quite certain that the largest principal stress is the one out of plane where we apply the confinement. So the reason why we could do this differently and have a preferential direction for fracturing, so to have an anisotropic stress state on the plane, from a pattern morphology point of view, it's more interesting if you don't have that. Otherwise, the fracture has a tendency to always develop in the same direction. So it seems less interesting to us.
I'm going to switch to modeling now, and that's probably the last two questions because one is sort of a three-part question that takes some time to read. So we'll start with the easy one first, or no, the short one first. From Omar Duran-Triana, regarding the multi-scale computation modeling, what are the critical points that need to be addressed in order to simulate such complex phenomena you describe in your experiments?
Okay, so I'm not sure that I've shown any multi-scale computational modeling here. I mean, the model that I discussed really was all at the pore level. So it was using a grain-to-grain contacts. So that would be, say, one network, the grain contact force network, and that is coupled with what you could think of as a dual network of the pressures at the pores, pressures and saturations or fluid the presence of different fluids at the pores, but it was all really at one scale. Yeah, we didn't use this as the grounds, say, for a computational model at a larger scale. So that would be an interesting proposition, but it's not something that we've done.
So questions keep coming on in. So I'm just going to start trying to read through that longer question, and then we see if we can take one or two more questions. So Hadi is the boss here. He's going to tell me when to stop. So Masamura, that's a three-part question. Thank you for the great presentation. I was quite impressed when I first saw, I'm going to mispronounce this, Burzan's model. Being able to predict flow rates and pressures does a lot to the picture. In the strong imbibition regime, as the dynamics is dominated by corner flow, I'd expect strong negative pressures inside the menisci close to the posts. Those pressures may lead to snap-over events. Somewhat similar to the Rayleigh plateau instability we see on the tap. Can that be incorporated into your model, perhaps adding fuses to the resistors and capacitors?
So that's a very good point. Hi, Marcel. So we haven't looked at that potential subsequent stability of the corner films. We have not, but there is good reason to think that they could occur, right? So the film, you are delivering fluid, it is coating, say, these posts along the corners, and these films are swelling. But once you have an avalanche event, you are delivering a lot of fluid in a short amount of time. So potentially, yes, some of those films could snap. So we have not incorporated that. Yeah, we haven't even thought about it.
Okay, so because there was a quick answer, I take two quick questions and hopefully with quick answers, and then we need to stop, unfortunately. King Wang Yan asked, viscosity ratio capillarity indeed play an important role. What do you think is the role of complex phase behaviors between injected fluids and crude oils at high pressure and temperature on fingering development?
Yeah, that's a great question. So everything that I've presented here, and really everything that we had done in my group until recently, really was restricted to perfectly immiscible fluids. Now, phase behavior or mass transfer between phases adds a really phenomenal layer of complexity into the picture. So all I can say, I'll say two things. First, that yeah, there's a lot to be investigated on that front, and we have taken some baby steps in that direction recently. I didn't present any of that, but there's some really surprising effects when you add evaporation and or condensation into these partially wetting systems. I don't have the slides or the time to get into that right now, but that's what I can say. So
We'll invite you next year again. Then
I'll be here.
I take the last question. Apologies to those we couldn't take any further questions. Mario Valavanidis says, great presentation. Thank you for the initiative. Ruben, could you please refer once more to the modified capillary number that you have introduced? Thank you.
Yeah, so the capillary number that we use is what we could say, we call it modified capillary number because it is the regular capillary number multiplied by a ratio of length scales. And that ratio of length scales is very different from one. It is the macroscopic length scale, say the radius of the cell, that macroscopic length scale to a pore-scale length scale, say the pore throat size or the grain size. So that gives rise to capillary numbers that are typically, let's say, loosely speaking, typically in the order of 1 instead of in the order of 10 to the negative 5. But we are borrowing that concept from others who've used it before, in particular, the Jorgen Malloy's group in a series of papers.
Okay, thank you very, very much, Ruben, again, for a great talk. Thank you, everyone, for excellent questions. Apologies if I couldn't take all your questions on there. Hadi, for some closing remarks.
Thanks to both of you and all the audience for the great discussion that followed after Ruben's talk. Many people have said hi to you, Ruben. I'm not sure if you noticed. Martin Blanc is one. I'm just seeing so many people are just saying hi to you, and hopefully you can catch up later with them. I would like to announce that our speaker of next week is Professor Philip Ringrose from NTNU, Norway, and he's going to talk about CO2 storage. Thank you all again. Ruben, it was great to see you. We wish we could see you in person, but we reserve that for next time soon, hopefully. And
thank you, everyone, and thank you for the initiative. It's a great thing that you guys are doing.
Of course, our pleasure. Thank you very much.
And see you all next week again. Thank you.
Thank you. Next week. Bye-bye.
Bye.